So what I'm going to try to do with the rest of today is to show you how to take the information that you've fitted from two-body scattering or information on the bound state pole and use it to compute electromagnetic processes on the two-body bound state. So the first thing we're going to compute is the charge form factor. So this is the first time I'm going to exploit the fact that I can couple photons to the particles that make up this bound state and predict and therefore work out how they're distributed spatially by probing the state as a function of momentum transfer. So the theoretical object we're going to use to do this is going to be a 3-point function. Sorry, wrong way around. We're going to create the dimer. We're going to hit it with a photon, and then we're going to annihilate the dimer. So this is going to be some sort of object like this. So if you think about this from sort of an LSC reduction perspective, you're going to have a dimer propagator here. You're going to have some object which I'll call gamma, which is going to depend on the index mu. And then you're going to have, I guess I'm going to have a photon propagator. Yeah, I'm going to have a photon propagator. So let me call that the gamma. And then I'm going to have another dimer propagator. If I do LSC reduction on this thing, I can get the amplitude, which we would often refer to here as our form factor, because it's the object that tells you how the structure associated with this object being composite changes the answer for this correlation function from something that's just what it would be for a point. So to work this out, we need to couple photons. So if we look at the nucleon part of the Lagrangian, we do that by doing minimal substitution. We have a time derivative. So we're going to send the time derivative to be replaced by the covariant derivative. We need to include the charges of the nucleons when we do this. So here I have I think this should be mod E. That's like the absolute value of the electronic charge, and then 1/2, 1 plus tau 3. This is just designed to give me 1 for a proton and 0 for a neutron. And then we're going to do the same thing for the gradient. The gradient gets replaced by, minus, because of different transformation properties, the gradient and the field times vector A. Okay, so then if I just substitute into the Lagrangian, now I'm going to generate a nucleon photon vertex, at least for protons. And I'm going to generate 2 types of vertices, depending on whether I'm talking about photons associated with the vector field A or photons associated with the zeroth component A0. So for the purposes of the first thing I'm going to do is I'm going to look at the charge form factor. So the charge form factor is the object that the electrostatic potential that's embedded in A0 couples to. So that means that I want to work with gamma 0. So the Feynman rule associated with A0 photons is going to just be that this now has a minus E times 1/2, 1 plus tau 3. In other words, it's minus I times mod E for the proton and 0 for the neutron. Because unlike the magnetic moments that Professor Kaplan was talking about this morning, this is just coupling to the elementary charge of the 2 nucleons. So then because we're thinking about gamma 0 as some sort of amplitude, conventionally we define it with a minus I, and then we draw we say that this is, in fact, it's this Feynman diagram that I drew there that we're going to evaluate, except amputated. So this is the object we're going to evaluate. We'll give the photon we're going to give the photon a 3 momentum q. So then we'll start off in the center of mass frame of the deuteron, where in order for it to be on shell as a deuteron, it has to have energy minus B0. So then here, this is minus B. Oh, sorry, I made a mistake. Let me start again. I want to put in my P0s. So we have one more opportunity to do a P0 integral. The photon here is, we're going to choose we're going to choose to have the photon be just carrying 3 momentum transfer. I'll explain how we can do that in a minute. And then here they come back together and we get minus B and then Q. Okay, so now maybe you see why I have to do some explaining, because if this is going to be on shell, it would actually need to have a kinetic energy Q squared over 2m. So this should be minus B plus Q squared over 2m, comma Q, because it has to, now it's carrying some 3 momentum because to satisfy 3 momentum conservation. But here the value of Q, is going to be much less than m, so we can neglect this recoil effect and work just with this as the final state kinematics. If this really bothers you, then you can choose a frame which is more symmetric, in which the deuteron comes in with momentum minus Q over 2 and goes out with momentum Q over 2. But this makes the Feynman parameterization, doing it this way makes the Feynman parameterization a little bit easier. Okay, so now we're going to do another one of these 4-dimensional integrals. I should say that here there aren't going to be any divergences at leading order, so it's predictive, and so that's why I don't have to worry about doing this in d dimensions. So I'll write down the bottom propagator first. So that's this one here. And then on the top line, I have the first propagator, I have the vertex, and then I have the second propagator. So now, if you sit here and stare at this for a minute, you will realize that I have 3 poles. Right? I have this pole here, and this pole here. But if we think about the I epsilons, only this pole is in the upper half plane and these 2 are in the lower half plane. So it makes more sense to close in the upper half plane and pick up this pole. And when we do that, we get what you might expect. We get the 2 non-relativistic propagators for these states, like that. Okay, so now I want to pause here and point out that what I have here is is the integral of two momentum space wave functions. If we had done this in non-relativistic quantum mechanics, we would have gotten something like the integral, the overlap of the wave function at P times the wave function after the injection of a certain amount of momentum. Actually, it's Q/2, as we'll see in a minute. And this suggests that if we want to interpret the dimer formalism as giving us access to the Deuteron wave function, the Deuteron wave function in momentum space will be proportional to this sort of Lorentzian structure. If that is not of interest to you, don't worry about it. You don't ever, if you just proceed in the field theory way, you don't need the wave function. But if you want to interpret what's going on here as involving a particular wave function of the two-body state, this is what the wave function would look like. Okay, so now I'm going to multiply through by a bunch of m's. And so I'm going to get, oh, and I missed the minus e, sorry. So now I have, if I combine this and this and this, I have I times e times integral d3p over 2 pi cubed. And then I have m squared, 1 over mb plus p squared, 1 over mb plus all right. And here I'm going to pull the same trick I pulled before. I'm going to replace, I'm going to drop the terms of order q squared because they're small. And so if I do that, I can complete the square here and write this as mb plus p plus q/2 all squared. So now I can use Feynman parameterization to combine these two denominators. And when I do that, I get that. So I think you're saying, yeah, okay, good point. So this should, okay, I didn't do this carefully enough going from here to here. So this should, so what you're saying is that this should be 2 MB. Yeah, so, right, so I should have done this step over here. So I should have done, okay, and then this is what I was saying over here, is that here I can complete the square, and the term that I omit is a q squared over, which is one of, it's the recoil effect. So actually this line is not true, but the next line is. So we'll just erase this one. Yep. Okay. So I should have put an X here, right? So here, once again, we're going to do some completing of the square. So p squared plus x p dot q plus x squared q squared over 4 minus x squared q squared over 4 is how we want to complete the square. And so when we do that here, and drop a minus sign over. No. Yeah. Okay, then when we get all right, so what I've done here is to complete the square on this. But when I do that, I have to pay the price of subtracting an x squared q squared over 4. But then I can combine that with this other q squared over 4 to give me this term here. Now, as you would do in a 4-dimensional calculation, you're going to shift the integration variable. And then this ends up being related back to an integral. And sorry, when I did this, I should have made this squared because it is convergent, right? So then we have 1 over mb. Now we're using it, let's call it p twiddle plus p twiddle squared plus q squared over 4 times x1 minus x, and this is all squared. So this integral is actually like, this is an integral you can just sit down and do. In the end, it's related to it's related to an arctangent, and when you do that integral, you're left with something that's a function of this, because this, like, you do the integral over p twiddle, but you still have this kinematic dependence on q squared left over, and you also have the mb left over. So if I call mb gamma squared, we can already guess the dimensionality here, because this is 4 powers of momentum downstairs and we have 3 powers of momentum upstairs. So we know that what has to appear here is this raised to the 1/2 power. And then the only question is the coefficient. So there's a 2 pi squared from the 1 over 2 pi cubed integrated over angle. And then there is a pi over 4 from doing the radial integral to get the 1 over square root thing. So I'll be honest, I just used Mathematica to do the radial integral. See, I did it by hand first, and then I used Mathematica to check it. All right. So this actually is our answer up to an integral over x. And again, if you ask Mathematica to do this integral for you, it will actually give you an answer that's not in the most useful form, but you can, how would I say that? But you can manipulate it using identities involving the arctan so that you get here. Oh, maybe this is a good moment to see. Yeah, maybe before I do that, I will do the wave function renormalization bit and actually extract the form factor. Okay, so this object here came from the unrenormalized correlator, if you like. So here we're just using this D field. We haven't multiplied by the wave function renormalization. So to get the physical gamma 0, we need to multiply by ZD. Now, I'm going to define an object which is actually the object that people extract in experiments, which is the charge form factor. And so gamma 0 here, the gamma 0 that I've defined here, that I'm computing here, this vertex, if I multiply this by ZD, and so I'm working with a physically normalized deuteron state, then this is equal to minus E times GC. So I have to do two things. I need to multiply this by ZD. So ZD times gamma 0. I carefully kept my result for ZD from over here. So I get 8 pi gamma over m squared g squared. And then I have IE m squared over 8 pi times my integral. Did I miss g squared somewhere? Yeah, I missed g squared, didn't I? Just excuse me while I find my factors. Oh, I missed the g's. This is how yeah, it's the vertices on the here. That was my mistake. So there's a minus IG from each of these. So sorry about that. So this is this divided by minus I g squared. So yeah, I'm going to change this to, yeah, this should have been plus. And so then, so ZD times, yeah. So then if we say that this renormalized gamma 0 is also equal to E, sorry, I'm messing up my normalizations here. I want this to be minus IE, because minus IE, that's, okay, sorry. That's the way to think about it. Minus IE is the vertex for an elementary particle. So if GC is going to be the modification of the vertex due to structure, then we say that this vertex, this properly renormalized structure object for the composite particle is the bare vertex minus IE for a particle of charge 1 times the modification GC. So minus IEGC is then equal to minus IE, the 8 pi's cancel, the g squareds cancel, the m squareds cancel. We have a minus IE on both sides, and we just have this integral to do. But we also have this factor of gamma left over. But the factor of gamma helps us to write this integral as a dimensionless, in terms of a dimensionless parameter. So we see that the form factor here should depend only on the ratio q squared over 4 gamma squared. So in other words, it's the square of the ratio of q over 2 to the binding momentum gamma. And if we, as I said, if I do this integral, I get 4 gamma over q times the arctan of q over 4 gamma. So this has, this looks like it could have problems as q goes to 0, but in fact it doesn't, because if the arctan goes to 0 as q goes to 0, so if we expand around q equals 0, we get 1, and then we get minus 4 gamma over q times q over 4 gamma squared times 1 over 3. Plus dot, 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 dot. Why did I bother to, so there are two nice features here. The first nice feature is that we have correctly found that the charge of the deuteron is 1. Right? So this form factor should go to 1 as Q goes to 0, because if I probe the structure of this object with an infinite wavelength photon, I should just see the total charge. So this physical vertex object should be minus I times E if we look at Q equals 0. And then this next term, as maybe some of you know, this is actually related to the radius, and the conventional definition by looking at the Fourier transform of the wave function overlap is that this is minus a sixth times the Q squared, the momentum transfer squared, times the radius. So we can use our result here to extract the radius. So compare to this expression. And so, as I said, we see two things. Number one, the charge of the deuteron is 1. That's not an earth-shattering prediction, but it means that we did something right in doing this calculation. In particular, we got the wave function. The wave function renormalization ensured that we got an overall 1 as Q goes to 0. And then number 2, the radius is equal to 1 over 8 gamma squared, if I did that right. This should be cubed. So yeah. Yeah, this I didn't, if I should either write Q squared, or I should write 4 gamma over Q times Q over 4 gamma cubed. So I should have done this. So then if I expand this out, I get 48, and then compare this to 6. So this is an 8. Okay, so now let's see, where do I want to go from here? I'm going to stop and ask if there are any questions. I'm sorry, can you say that? Because I'm just, the photon here is classical, right? It's just right. I'm not, I mean, we didn't try and do anything fancy like dress the photon with a vacuum polarization. So all I'm doing, you could think of, all I'm trying to do is extract the current that photon couples to in some classical sense. Okay. Yeah, I could do this as a background field calculation, indeed. Yeah, yeah. But I have to give my background field a finite momentum if I want to extract the form factor at finite momentum. Right, so I could only use a constant background field to get the form factor at 0, in which case I should discover that it's 1. Other questions? Yeah. Because I'm going to do that, because this is leading order. So we decided that the kinetic term of the dimer was a next to leading order effect. Yes. So that's exactly what I'm going to do after I take questions. And so you can already think about how this calculation would change if we had a dimer with a kinetic term. So while if you don't have a question and you just want to sit there thinking about something, you can think about the way in which this calculation would change if I do it for a dimer with a kinetic term. Okay, other questions? All right, well, sorry I missed the factor of minus IG at first, but I think, and I didn't have this written down correctly, but I think in the end we got there. Okay. Let's talk about, so this is a leading order calculation because we just used the static dimer, which reproduces the effective field theory result at leading order. And now we're going to do next to leading order. I'm going to try and figure out what I want to erase. I want to keep that. I think I'll erase this and just start here for the moment. All right. So since you had a few minutes to think about it, what changes when I do the calculation at next to leading order? Excellent question, right? So suppose that so if we look at the dimer Lagrangian, which I guess I don't have up here anymore, the dimer Lagrangian, once it was dynamical, looks like this, right? So if the dimer is not dynamical, then we don't have to worry about minimal substitution on the dimer Lagrangian. But if the dimer is dynamical, we do. So here we generate new vertices. So there's going to be a minus d dagger y a0 d. And then if we were working with the photons associated with a vector, then we would also have plus y nabla minus I e a squared. Sorry. And we'll see that actually these contributions are crucial for charge conservation. All right, so what is this vertex? This is a very easy vertex. It's just minus I. Oh, I forgot the e's, didn't I? Sorry. Mod e times y. So what else? What else changes? I can ask a leading question. Does the diagram that we actually calculate change? We have to calculate two diagrams, as was just pointed out, right? But does the structure of this loop change if we make the dimer dynamical? We can have a vote. Okay, so what do you have a suggestion? Okay, so I have no photons in my Lagrangian, right? My photon is just like an external field, right? So, well, actually, I should be careful. I have no dynamical photons. The only place the photon appears is here. You should think, the way to think about this is that this is an external field, and we are trying to assess the coupling of the system to the external field, right? So, yeah. So if you think, so the vertices this is the kinetic part of the dimer Lagrangian, and this is different between, so this is leading order, and this gets added at next to leading order. But this part of the theory doesn't change between leading order and next to leading order. There are no momentum dependent or energy dependent vertices with the dimer, which can get gauged. So, and the nucleon part of the Lagrangian is the same between leading and next to leading order. So the diagram itself here is exactly the same in the leading order and next to leading order calculation. Or to be more accurate, we calculate that diagram and then we add to it this diagram. So I'm pacing, I guess we don't need all the details anymore. But there's something else we did that does change. We had to multiply by the wave function renormalization to get this result. And the wave function renormalization is different at next to leading order. Because if you look over, suppose you look all the way over here at this propagator, this is one reason I left this up here. So at leading order, you just have this. So you find a pole, you compute the residue. That's what we did when we computed the wave function renormalization before break. But if I'm doing next to leading order, then I have this different structure downstairs and I'm going to get a different residue. So what we have to do here to do this calculation at NLO. So at NLO, we're going to have minus IEGC is equal to ZD NLO times this result with the extra factor of G squared. So I don't know exactly where we should come in here, but like times G squared times minus IG squared times IE M squared over 8 pi integral 0 to 1 dx 1 over the square root of gamma squared plus q squared over 4x1 minus x. In other words, we can write down the same loop diagram, go through all the same steps, but the point where things change is when we take the result for this loop diagram and multiply it by the wave function renormalization. And then the other thing that happens is we also have to include this minus I mod E. I'm being a bit inconsistent about whether I write mod E or not, times Y. And that's also going to get multiplied by the wave function renormalization at NLO. Sure. Because now I'm trying to compute the form factor at NLO. So including the range corrections, right? And yes, I'm doing a different, if you like, it's a different calculation. So I'm saying that when you go to NLO, the diagram in which the photon couples to the proton inside the deuteron doesn't change, but it does acquire a different wave function renormalization factor. And you have to include this effect that you pointed out, that there's a short distance coupling mandated by gauge invariance. The what is coming? The Y is coming, yeah. So this is, if you Fourier transform this, this is actually a delta function. This is a contribution to the deuteron charge from the dimer itself. So it's a contribution to the deuteron charge at R equals 0. We're going to do, like Sumit suggested, that we take the propagator and we write it as the pole times the residue plus regular stuff. So if we want to live at the deuteron pole, we're going to want to include all the effects of the range on the wave function renormalization. Okay. So we need to compute the NLO wave function renormalization. So the propagator, I'll just copy from over there so I have it over here, is, how did I write actually? Yeah, okay. So the propagator is, without the G squareds, is I over delta plus Y K squared over M plus I MK G squared over 4 pi. So I can use those relations that I have reserved over there to pull out, if I pull out a factor of G squared, I can write this as 1 over M over 4 pi A minus R0 M K squared over 8 pi plus I MK over 4 pi. So then, just to make the pole structure explicit, this is 1 over A minus R0 K squared over 2 plus IK. So we're going to be looking for poles of this, which really means we're looking for zeros of the inverse amplitude. So for those of you who studied this in quantum mechanics, this may be familiar. So we're going to look for poles of the inverse amplitude, and we're going to look for poles that are on the positive imaginary axis. So we're going to solve for poles with K is equal to I gamma, where gamma is this thing I keep writing down, the square root of m times b is the binding momentum. So that means we're going to have to solve a quadratic equation. There are going to be two solutions because it's a quadratic, and this is related to this issue of the spurious poles that I mentioned before, or the spurious pole. So if you solve that quadratic equation, you get gamma plus minus equals 1 plus or minus the square root of 1 minus 2 R0 over A over 2 over R0. So the root with the plus sign is a binding momentum of order 2 over R0. And since R0 is 1 over R0 is a high scale, the gamma plus is outside the domain of validity of the EFT. And the one with the minus sign is the one we want. So in order to make progress, I'm going to factor the quadratic. So I'm going to say that this is I over G squared 4 pi over M. I'm going to pull out the factor of R0 over 2. And then I have 1 over, and I have 2 poles. So I have the deep pole, and I have the pole we actually want at K equals I gamma. And then I can do the same trick I did before the break and multiply top and bottom by K plus I gamma, although here I only want to do that for the shallow pole. And I get a form where this is I over G squared 4 pi over M minus 2 over R0 . Okay, and then hopefully by now you remember that this K squared plus gamma minus squared is what we want, because K squared plus gamma minus squared is up to a factor of M E plus B. Now we actually get another M squared here. We still have minus 2 over R0. And then what I'm going to do here is evaluate this at the pole at I gamma minus. So I get 2 gamma minus over gamma minus minus gamma plus. And then I get 1 over E plus B. And then everything else is regular because I've made my Laurent series around the bound state pole. It's not regular all the way out, but it's regular around the pole. So this doesn't immediately look like our wave function renormalization before. So because we want to say that this is I, Z, D, and LO divided by E plus B plus regular. But if we do a little bit of work, we can start to see the other one emerge. So ZD and LO is going to be 8 pi gamma minus over G squared M squared. So that part is the same as before. And then the other part is this minus 2 over R0, 1 over gamma minus minus gamma plus. We're almost there. So gamma minus minus gamma plus is, you just take the difference of these two roots. So if you do that, you get minus 2 over R0, the square root of 1 minus 2 R0 over A. So this factor of -2 over R0 cancels, which is good because we want the wave function renormalization to be positive. Otherwise, it's a ghost pole. So this is 8 pi gamma minus over g squared m squared times 1 over the square root of 1 minus 2 R0 over A. So an interesting fact here is that the ratio, if you like, the effect of the finite range is to enhance the wave function renormalization above its leading order value, because R0 is positive and A is positive for this bound state. And so this number here is going to be a positive number. We're going to get the denominator smaller than 1, and then this is going to be bigger than the leading order wave function renormalization. There's actually a simpler form of this, which I'm going to utilize. The simpler form comes from realizing that there's an identity here that 1 over A can be replaced by gamma minus R0 gamma minus squared over 2. And when you substitute this in here, you have a perfect square downstairs. You have the square of 1 minus R0 gamma. And so a simpler form for this is just that it's ZD leading order divided by 1 minus R0 gamma minus. And for those of you who are interested, numerically, this factor is about 1.65. So this is not a small correction. We had a couple of discussions over coffee yesterday about Weinberg's compositeness argument. So this is my understanding of the factor that Weinberg computes is this ratio of higher order to leading order wave function renormalization. The wave function renormalization at leading order is interpolating field dependent, but if you compute this ratio because you use the same interpolating field at the 2 orders, you discover the effects of finite range, and in this case, they enhance the wave function renormalization. All right, so now we have all the pieces we need to do our calculation. We already know how to do this integral. We have the next to leading order wave function renormalization, and we have relations that connect y to physical observables. That's, for example, we need this relation here. So we see that y, there's going to be some term, the term proportional to y is going to become a term proportional to R0. So let me just write down the answer. So if you put all this together, you discover that this charge form factor at next to leading order is 1 over this enhancement in the wave function renormalization times the leading order form factor. Now, before I go any further, let me ask you a question. What did we get for the charge of the deuteron here? Just at leading order, the charge of the deuteron was 1. This number is larger than 1. So if we didn't have something else, we would have violated charge conservation. But we do have something else. If we do U1, if we do current conservation properly through minimal substitution, we get this extra piece, which is y times ZD NLO. And by now, I'm sure you're fed up with seeing me do algebra on the board. So I will just tell you that if you substitute in the result for ZD NLO that we computed over here and the result for y that's over there, you discover that this is this gives a correction that's a constant, just minus R0 gamma divided. And so this whole result can be written as now we see that the fact that this goes to 1 as q equals 0 means that we have the 1 minus R0 gamma in the numerator and 1 minus R0 gamma in the denominator. But the interpretation here is a little funky. The long distance part of the form factor actually gives us a norm that's larger than 1, a charge that's larger than 1, and then this is corrected by a negative contribution to the charge density that sits at the origin. This is related to this picture where this wave function is all tail. So if the wave function is all tail, we actually have integrated the tail part up to something that's larger than 1. That's mandated by the normalization that comes from doing the analytic continuation from the pole. And then because we lied about short distance physics, the minimal substitution saved us and said, well, okay, if you're really going to take this all the way into 0, you're going to need some negative contribution to the charge density in order to correct for the fact that the wave function doesn't really do that in here. If there was some potential involved, the wave function would actually do that. You need to correct, you push this all the way into r equals 0, and to correct for that, you need some negative contribution to cancel the mistake you made here. And here, you don't need to fit the negative contribution to data because charge conservation tells you exactly what the negative contribution has to be. So the symmetry, the U1 symmetry, if we want to be fancy about it, protects you from it protects charge conservation, so it makes a prediction for what this short distance piece has to be in order to preserve the symmetry. I'm sorry? Exactly. That's the next calculation. So you are either, maybe we can say that both things are true. You are doing a great job tracking, and I am clearly doing a great job lecturing because you are asking exactly the question that leads me into my next thing. So yeah. So if any of you ever, for those of you who've taught, you know that this is exactly what you want. You want the person to ask the question that's like, that's an excellent question. Let's do that now, right? So, okay. So the change in the charge radius is actually pretty easy because this doesn't contribute to the charge radius because it's all at r equals 0. So the charge radius just gets enhanced by this factor of 1.65. So now I'm going to have to tell you something that you're just going to have to believe, right? Which is, so this is the expectation value of the relative coordinate. When people talk about the charge radius of the deuteron, they actually measure the position. They're talking about the position of the proton in the deuteron. And because the relative coordinate is Rp minus Rn, there's a factor of 2 between the two of them. So if I talk about R squared to the 1/2 experiment, this is actually 1/2 the square root of this, or we should compare to this, because the experimental number is like a proton radius, not a relative radius. So if I sat down and worked this out earlier this morning, and this number, 1/2 the square root of R squared NLO, is 3.95 Fermis. And the experimental number, there are 2 different experiments, depending on whether you do it from spectroscopy or by measuring electron deuteron scattering. Electron deuteron scattering gives 3.936 with an error of 12 Fermis, and spectroscopy gives 3.95014 with an error of 56 Fermis. So this calculation works remarkably well, probably better than we really had a right to expect. But I think the thing that actually works in our favor here is that there are no additional corrections to this charge radius until you hit a short distance operator that is not protected by charge conservation. So something like this, where this basically it's like Q squared times A0. So it gives you something that exactly looks like a piece of the short distance piece of the charge radius that you have to fit. So this is like the reason, if you want to think about a physics reason that this works because you're computing the expectation value of R squared. And so when you look at this probability density, you're weighting this with R squared. So if you went ahead and computed even higher moments of the deuteron probability density, they should be even more accurate, because the further you weight out in R, the more accurate this EFT is, because it gets the long distance physics correct. All right. I was going to talk about gamma D to NP, but I think my time is up. So I will stop, and then we can do questions after a break, right? Yeah, first, like if you have questions about this calculation, this would be a good time to do it. People did that.
Can I take this? I mean, so take the constituents and the composites, keeping them sort of on equal footing.
Yep.
And getting something non-trivial like that.
Yep.
For any, let's say, two-body bounds.
That's right. So you could.
Can I do that?
Yes, so you could totally do this for anything. That's right. So you could do it in like for the X3872. What it is, right? 3872, that's the number, X. Yeah, or you could do it in, so with collaborators, I've done analogous calculations for halo nuclei. So the only real difference there is that maybe both constituents are charged,
yeah,
right?
Yeah.
And
So
they have, they have different masses. But these differences are essentially trivial, right? The formalism just goes over. I will say the one thing you need, which can be somewhat tricky for unstable nuclei, is that you need measurements of R0, right? So this here, we relied on the fact that we have experimental data on the effective range to get the Z factor. Right? If you don't have experimental data on the effective range, you may end up actually using information on structure observables to get the Z factor and then effectively predicting the effective range in scattering. Because it's very difficult to do, for example, neutron scattering on some unstable target, but maybe you're interested in what happens when they form a bound state. Right? So this, for example, like, I don't think there's any scattering data on neutron carbon-18 scattering, but there is data on the structure of carbon-19. So then you basically have to use the data on the structure of carbon-19 to infer what the scattering information would be.
You need weakly coupled bounds.
Well, so you're saying they have to be not deep compared to the mass.
Explicitly non-relativistic.
That's right. So if your bound state was bound by a significant fraction of the particle masses, then I think certainly some things would change, right? Whether you could, like, I think the problem with that is like, for this is the reason that it might be difficult to find a case like that where this formalism was applicable is that you, of course, also have to assume that the state is weakly bound compared to the range of the force, right? So that honestly is the one that...
That's the key, weakly bound compared to...
That's right. So that's the one that usually gets you rather than a non-relativistic one. Because the scale lambda is usually significantly lower than the scale m. Yeah, hi. You can absolutely do them, and I can send you to the literature where it's done. So yeah, so the first people to do the calculation the way that I did it here were actually Bean and Savage, but there was a calculation even earlier by the aforementioned Rupak and Chen and Savage, where they did the calculation essentially using like C2s and stuff rather than dimers for the charge, quadrupole, and magnetic form factor. And then they also did, those three guys did NP to D gamma before Rupak did it to higher order. So, yeah. Okay. Yes, okay. But so F1 and F2 and F3 is the relativistic form factor, right? So here I tend to use the non-relativistic decomposition of the deuteron current into GC, GM, and GQ rather than the relativistic one. Just for the reasons we're saying, these are, non-relativistic bound states, small momentum transfer. So writing things in terms of a non-relativistic current and charge operators is maybe a little more natural rather than going over to like the relativistic spin one field. Yeah. Right. So to get a non-zero quadrupole moment in this formalism, you need to consider that SD mixing operator that I was discussing before. But in fact, in this, so let me think about. I have to check how this goes. But at first blush, I would say that you want to do something like, I used an oval before, right? This one plus the photon on the other loop. So the idea here is that the photon couples and then you get some, oh, actually, sorry. Yeah, and then you, but the couple, but this, you think about this as the D wave component of the deuteron. So this operator induces a D wave component perturbatively in the deuteron, and the photon, because as you say, we think about the quadrupole part of it, the photon can induce transitions between the big S wave part of the deuteron and the perturbative small, but there at n squared LO, D wave part. So if I remember correctly, the quadrupole form factor is, it's the leading contribution is predictive. And then after that, you hit a short distance operator. So basically the E2 photon, it's like some epsilon dot q minus 1/3 epsilon squared q squared. The photon, the E2 photon can just couple directly to the dimer, right? I'm sorry, I got that wrong. I do epsilon dot s. So then the photon can couple directly to the dimer without needing to go through a D state. Because this statement that you have to have a D wave is only strictly true if you demand that it happen via a one body operator. You could have two body operators like that that allow a quadrupole photon to change the spin of to interact with the spin one of the deuteron. Yeah. And again, this is to echo what David was saying. This is a strength of the effective field theory, is that when you compute the deuteron quadrupole form factor beyond its leading order, you find a divergence, and that tells you that there has to be some short distance mechanism that cancels that divergence. In that case, because E2 photons are not protected by charge conservation, you need to fit that number to data. But you fit it to, say, the quadrupole moment, and then you still have a prediction for the quadrupole form factor. Okay, so yeah. Yes. Yeah, so this is an interesting point, right? So I didn't go into this because this is a bit of a technical detail, but when you do this matching, you can either choose to do it at 0 or you can choose to do it at the deuteron pole. And if I had done it at the deuteron pole, I wouldn't have had to play this game where I replaced R0 over A by R0 gamma. That would have just come out straight away. Right. So in that case, the NLO effect, actually, it's very clear, like if you match at the deuteron pole, then your leading order parameter gets the pole in the right place, and your next to leading order parameter gets the residue correct. So this is exactly what I was saying, right, that you can think about it either way. You can either go from the scattering regime to the bound state, so you can renormalize around zero positive energy by getting R0 and A, and then you can predict the bound state properties, or you could renormalize at the bound state pole and predict the scattering observables. It's just a choice of renormalization point, but the EFT relates what's going on in the positive and negative energy regime. Really, it's analyticity, but the EFT has analyticity baked into it. Okay. How long do we want to break for?